Hello, my dear students. Welcome to IKSR chemistry classes. In this video, we are going to discuss dissolved oxygen and its significance under the chapter Skill Development. First of all, the question arises in our mind: what is dissolved oxygen? Let us see the definition of dissolved oxygen, which is abbreviated as DO, the amount of free oxygen, that is elemental oxygen O2, present in the specified amount of a water sample under given conditions of temperature and pressure, is called dissolved oxygen, which is abbreviated as DO. DO is more popular term than dissolved oxygen. Let us see it again. The amount of O2 present in the specified amount of a water sample under given conditions of temperature and pressure is called dissolved oxygen. Representation: the dissolved oxygen, that is DO, is expressed in terms of milligram of O2 present in 1 liter of water sample, which is also called ppm. The dissolved oxygen in a given water sample is expressed in terms of milligram of O2 present in 1 liter of the water sample, and 1 milligram O2 per liter of the water sample is equivalent to 1 ppm, 1 part per million of O2 in the given water sample. Solubility of oxygen in water. Oxygen is only slightly soluble in water as per the statement like dissolves like. It means polar solute dissolves in polar solvent, while non-polar solute dissolves in non-polar solvent. Water is a polar solvent, while O2 is a non-polar solute, and hence O2 dissolves in water only slightly. This is non-polar O2 molecule. But H2O molecule is polar. When O2 molecule comes in contact with polar H2O molecule, the O2 molecule is polarized. Dipole moment is induced within O2 molecule by H2O molecule, which has permanent dipole moment. The dipole induced in non-polar O2 molecule is called induced dipole, while H2O molecule has permanent dipole. Now, a weak attractive force acts between induced dipole and permanent dipole, which is called dipole-induced dipole interaction. The attractive force acting between O2 and H2O is dipole-induced dipole interaction, which is a very weak force, and this is why O2 dissolves only slightly in water. Importance of dissolved oxygen. The presence of dissolved oxygen is essential to maintain the higher forms of biological life in water. It maintains the balance between various populations in water bodies. It makes water bodies healthy, and the chemical and biological processes taking place in a water body are largely dependent on the presence of oxygen. These are the importance of dissolved oxygen, and now the sources of dissolved oxygen. The main source of dissolved oxygen is from atmosphere. The water waves on the surface of water lead to dissolution of atmospheric oxygen in water. It is called aeration process, and the photosynthetic processes of green plants underwater also contribute to dissolved oxygen. The main source of dissolved oxygen is atmosphere and photosynthesis by underwater plants. Water waves leading to dissolution of oxygen. This is a beautiful lake. Water waves arise on the surface of water due to the flow of wind. As a result, O2 comes in contact with the wave and dissolves in water. This contributes to dissolve oxygen. The water waves lead to dissolution of atmospheric oxygen into water. Aerators are used in aquarium to dissolve O2. This is an aquarium which has aerator which passes air through its water in the form of bubbles, and as a result air comes in contact with water to a greater extent and the solubility of O2 in water increases. It contributes to dissolved oxygen in the water of aquarium. Photosynthesis underwater. The photosynthesis by green plants which are submerged underwater also contributes to dissolved oxygen. During photosynthesis, the underwater green plants assimilate oxygen gas and releases oxygen gas. During photosynthesis by underwater green plants, CO2 gas is assimilated and O2 gas is released to water, which dissolves in water to some extent and contributes to dissolve oxygen. At the same time, O2 diffuses from atmosphere to water and dissolves in it to some extent, and wind cycling carries this dissolved oxygen to the lower portion of water body, and thus oxygen is present everywhere within a water body, at the top and at the bottom also. The fountain or spring water contains greater dissolved oxygen than any other water because air is mixed up in it thoroughly. In a fountain or spring, water falls from the top of a hill to its bottom. During this process, air is mixed up thoroughly in water, and such water contains higher dissolved oxygen. This is a beautiful fountain in which water is falling from the top of a hill to its bottom. During this process, water is mixed up thoroughly with O2 and dissolved oxygen increases. Factors affecting dissolved oxygen. Water is a liquid while O2 is a gas. O2 dissolves in water forming aqueous solution of O2. During this process, a small amount of heat is released and thus it is slightly exothermic process. The DO, that is dissolved oxygen, depends upon the following factors. First one is temperature. If temperature is increased on this equilibrium, the equilibrium will shift in that direction which leads to absorption of heat, that is decrease in temperature. In the present case, if the temperature is increased, this equilibrium shifts in the backward direction so that heat is absorbed. It means when temperature is increased, O2 dissolved in water comes out from it. That is, the dissolved oxygen decreases with increase in temperature. The second factor is mineral content of water. As the mineral content of water increases, DO decreases. It can be understood with an example. If we add common salt to cold drink, CO2 gas dissolved in it comes out in the form of bubbles. The solubility of any gas in water decreases with increase in its mineral content. This is why the DO value of seawater is lower than that of fresh river water. And the next factor affecting DO is partial pressure of O2. This is Henry law equation. Partial pressure of O2 over its saturated solution is equal to KHO2 into mole fraction of O2 in the solution. If O2 gas is in equilibrium with its saturated solution, the partial pressure of oxygen over the solution is equal to the product of Henry law constant of O2 and mole fraction of O2 in the solution. It is obvious that Kh, Henry law constant, is constant for a given gas at a given temperature. As the partial pressure of O2 increases, the mole fraction of O2 in water will also increase. It means the solubility of oxygen in water increases with increase in partial pressure of oxygen. This is oxygen gas which is in equilibrium with its saturated solution in water. If the pressure of oxygen is increased by putting more heavier weight on the piston, some O2 molecules go to the solution and thus the value of dissolved oxygen increases. The value of DO decreases with increase in temperature and increase in mineral content of water, while the value of DO increases with increase in partial pressure of oxygen. Henry law constant. We have already seen this equation. Partial pressure of O2 over the saturated solution of oxygen in water is equal to Henry law constant of O2 multiplied by mole fraction of O2 in the solution. This is constant for oxygen gas at a given temperature. As the pressure of oxygen increases, greater amount of oxygen will dissolve in water. As the pressure is increased, greater amount of oxygen will dissolve in water and the value of DO increases. It means the value of DO is directly proportional to the partial pressure of O2 gas. The mole fraction of O2 is equal to number of moles of O2 in the solution divided by number of moles of water plus number of moles of O2. KHO2 is constant at a given temperature for a given gas. Therefore, as the partial pressure of O2 increases, XO2, that is mole fraction of O2 in water, that is solubility of oxygen in water, increases. If the value of KH increases, for a given pressure of O2, XO2 will decrease. That is, the solubility of O2 in water will decrease if the Henry law constant increases. The Henry law constant for O2 gas at two different temperatures are given here. At 293 Kelvin, KHO2 is 34.86 kilobar, while at 303 Kelvin, the value of KH for O2 is 46.86 kilobar. It is obvious that on increasing temperature, the value of KH increases, and on increasing the value of KH, the solubility of O2 in water decreases. This is why the solubility of O2 in water decreases with increase in temperature. Graphical representation of the facts discussed earlier. It is fresh water and the green line is for seawater. This is DO value in ppm increasing in upward direction, and here we have temperature. On increasing temperature, the DO value decreases. And another fact is also evident from this figure, that the DO value of fresh water is greater than that of seawater. Seawater has higher mineral content and hence lower DO value. And this is another graph in which DO has been plotted against altitude. As the altitude increases, as we go above from the Earth's surface, the partial pressure of oxygen decreases, and therefore the DO value also decreases. DO decreases with decrease in pressure. As we go higher from the Earth's surface, the partial pressure of O2 decreases and hence DO also decreases. As the temperature is increased, the DO value decreases. At the same time, the DO value of fresh water is greater than that of seawater. DO and indicator of water quality. Greater the DO value, healthier is the water body. Greater the DO value, less polluted is water. The DO value in fresh water at room temperature and pressure is about 8 ppm. Under normal conditions, the DO value in fresh water is 8 ppm, that is 8 milligram per liter of water. As DO level in water drops below 5 milligram per liter, aquatic life is put under a stress, and the lower the DO, greater the stress. Oxygen levels that remain below 1 to 2 milligram per liter for a few hours can result in the mortality of fish on large scale. It means if the DO value in a water body remains below 2 ppm for a few hours, the fishes will die. Requirement of dissolved oxygen in ppm by some freshwater organisms is given below. Bacteria can survive in water even in very low DO value, while trout requires very high DO value in water for their survival. These are different freshwater organisms which require increasing amount of DO value. And now the time for homework. On the basis of previous discussions, you can solve this homework easily. Calculate the dissolved oxygen in milligram per liter, that is in ppm, at 30 degrees centigrade at an atmospheric pressure of 1 atm if air contains 21% O2 by volume. Air contains 21% O2 by volume and the atmospheric pressure is 1 atm, the temperature is 30 degrees centigrade, then we have to calculate the dissolved oxygen in milligram per liter. This is a very easy, quite easy problem. You can solve it very easily if you have understood the previous discussions clearly. Thank you for watching the video with concentration. Please like and share it. If you have not subscribed my channel yet, please subscribe it so that you may get information regarding my new videos in time. Thank you again.